can you guys hear me? Okay. Yeah, hi, so I'm Maaz from University of Washington, and today I'm going to be presenting my work that I've been doing in collaboration with Elwin Chang on basically translating sequential Java code to MapReduce frameworks. So first of all, why do we care about this, and why do we want to translate sequential code to MapReduce? Suppose you have an existing Java sequential implementation of some program, and you'd like to be able to optimize it. So this could be code that you wrote or some code that you inherited, but now you want to make sure that this code can process more data, or maybe you want to make it run faster, so you want some kind of distributed or parallel computation. The good news is there's a lot of tools and frameworks that have been developed by the community that allow you to build scalable and efficient implementations of applications. The problem is you can't just take your existing sequential application and run it on these frameworks. You actually need to rewrite your application so that it uses the MapReduce API that they expose. So at this point, you as a developer have one of two options. A, you could just throw out the old application and try to rewrite it using the API. But this is hard. It's tedious. You can introduce errors into your existing code. And also, this will require expertise both in understanding the target framework as well as understanding the algorithms that go into the original application. So the other approach that you can take, which is the one that we're sort of proposing here, is to build a compiler to automate this process. So the second thing I want to talk about is why is this an interesting and challenging problem to solve? So if I give you an overview of how compilers generally work, you basically have syntax-directed translation. What this means is you define a set of code pattern matching rules. So here is one rule which says match all for loops that are doing a filter. In this case, the in and the out can be any Java expression that is of a type list. So then the compiler would scan the input code looking for code patterns that have exactly this syntactic form. And if you find a code fragment, you just use a rule to convert that into a filter operation in the target language, let's say Spark. The problem is, if your code has just these simple code fragments in this nicely written form, you can define these rules. But in the real world, you have more complex code fragments. So here's a simple implementation for the PageRank algorithm doing n iterations. And the set of rules that you need to translate this to MapReduce, it's not obvious. Even if you were to design a set of rules that could do this translation, those rules would still probably be very brittle to code pattern changes, and just some syntactic changes might break them. So therefore, we present a different approach. So we know we can't translate Java code because Java is this complex and large language. So let's make the problem simpler. What if instead of Java, the input program that we want to translate was written in a much simpler, much cleaner, and much smaller language that had the MapReduce primitives? Now, of course, if you have this program, generating Spark code is easy. It's basically already a MapReduce program. You just need to use the right API calls. Of course, nobody writes a program in that toy language, so we need a way to basically bridge this gap. We need a way to lift the Java programs into this high-level representation that we have. And to do that, we use program synthesis. So what is program synthesis? Consider again, we have the same PageRank algorithm that we want to update. And consider this shape to represent the space of all possible programs that you could write using MapReduce operators. Now, within this large space, there's bound to be one or more algorithms that are actually implementing PageRank. So they basically compute the same outputs over the same inputs. Instead of using rules to do the translation, we simply search this space until we can find one of these translations that have the same outputs generated for all the same inputs. And we can check that they compute the same outputs using a theorem prover. To first approximation, you can think of the search algorithm as just an exhaustive enumeration of all possible programs in this space. Now, the exact algorithm that we use to search the space or how we check the equivalence is not something I'm going to talk about, but you can find a detailed overview in the paper. What I instead want to talk about is the more interesting problem of how do we actually make the search practical. So of course, this is an exponential space. How can we search it in any reasonable amount of time? So I want to talk about a few key insights that we have. The first is to use or design a very concise API to express these intermediate specifications. Of course, you could just directly search for translations in the Spark API. But Spark, for instance, has over 80 high-level operators, and these operators often have similar or overlapping semantics. Searching in that space is hard, but you can sort of drill that down into just a few key operators, map and reduce, that you can use to capture the semantics. And then once you have that intermediate representation, you can generate the target code. The second insight is to use static program analysis. So what this means is we look at the input code and we try to automatically detect a few properties about it. For example, we might look at what are the operators being used, what are the library functions being used, what are the variables in scope. And using all of this, we can specialize the search space. So we may not search all possible programs. We may only search programs that use the same operators and the same library functions. The third idea is to use incremental search. And the idea here is that instead of searching the entire space at once, you partition it down into smaller chunks. And you can do that based on different MapReduce properties, for example. So we search for programs that use 2 MapReduce stages before we search for 3 or more MapReduce stages. And the final idea is to use cost-based pruning. So if we can order these search spaces based on the quality or the cost of the solutions that they generate, then we can search for spaces that have faster solutions first, and that will allow us to prune away some of the search spaces and never even have to search some of the compartments because we already know we have a better solution from the cheaper search space. So all of this that I've explained to you, we've implemented in a tool called Casper. Casper takes completely unannotated Java source code, and it will generate a new version of the application that can be optimized using either Spark, Hadoop, or Flink. So we've tested this on about 55 benchmarks. These are all kinds of classical MapReduce problems, mathematical and statistical functions. We also did some iterative workloads and also some image processing algorithms. The thing that I want to emphasize here is that apart from a very few benchmarks which are synthetic and they were used to show a certain property, most of these were taken either from prior work or their open source code that we've translated. So does it work? Out of the 101 code fragments that we found that were amenable to be translated, we were able to automatically translate 82 of them. And the ones that failed were either because we timed out, so the search took just too long, we had a 90-minute timeout, or some of them could not be expressed in our intermediate language that we were using. So how well does it work? So the first comparison that we wanted to do was with a rule-based compiler. So Mold is some prior work that tries to do the exact same translation from Java to MapReduce, or Spark specifically. The problem is it was not an open source tool, so we could only compare against the algorithms or the code fragments that they did in their own evaluation. So for a more satisfying comparison, we hired 3 freelancers from an online platform, and we had them translate all this code manually. So now this graph shows the speed up obtained over this, the sequential programs by both the hired developers and our automated tool. And as you can see, in most cases, the performance difference is very negligible. There are some cases like the 3D histogram where they exploited some knowledge about the domain or some knowledge about the specific algorithm to make it more optimal. The last thing I want to talk about is how long does it take. So on average, one benchmark takes just under 12 minutes to synthesize. And the median time was just 2 minutes. So for the simpler benchmarks where pruning really comes into effect, we can find solutions really fast. And of course, there's also no managerial overhead. You don't have to email people asking if they've translated your code already or not. So it was much easier to work with Casper than it was to work with freelancers. The final takeaways that I want to give you is that Casper is a tool that can translate a wide array of sequential applications. And with an average speed of 15.6 seconds, it's competitive with handwritten translations. So this tool is completely open source. We have a demo online that you can check out. Yeah, thank you.
Great. Can you give an example of one of those programs that you mentioned that they failed, that you couldn't translate?
Yeah, so I don't remember the exact algorithms that they were, but basically the idea was that if you have something, let's say 5 or 7 MapReduce stages. So basically what makes the problem difficult is how large the translation is. I would want to mention one thing though, is that we translate at a code fragment level. So it can be a large application with 100 different code fragments, and we can translate that. But each individual code fragment, there are limits to how large can it be, or how large the translation can be.
Thanks.
Thank you.
Seems like rocket science. Can you qualitatively explain what was not translatable before that Casper has translated, and what might still be translatable but Casper can't translate today?
Right. So if we're talking in a theoretical point, from a theoretical standpoint, any code fragment can be translated if you have the right set of rules. The problem is not that it's impossible to come up with these rules. It's really, really difficult. And the other problem is that these rules are very brittle. So you can imagine writing the same algorithm with different syntax, and the rules might not work because they rely on pattern matching. So the real strength that Casper gives you is it doesn't really care about syntax. It's dealing with semantics. So you can write your program with any Java syntax, and it will be able to search for the translation. So really, in an ideal or perfect